Our guest today is Professor Tony Vannelli. You may know him as the provost and vice president academic, but today Tony is joining us as professor in the Department of Physics and Computing Sciences in the Faculty of Science on our Waterloo campus. Welcome, Tony.
Oh, thank you, Jonathan, and thank you for having me here, and welcome to everyone. Thank you for listening to me today.
So let's just start off with some background, Tony. Can you tell us about how you came to be working at Laurier?
Great question. I think I'll give a short answer, maybe a slightly longer one. The short answer is I really like to be in places that really like to create things or are moving in directions where they challenge boundaries. To this point, I've been in institutions, certainly with the University of Waterloo for 20 years up the road. But then about 15 years ago, I consciously made a decision, not only as an administrator, because I've had administrative roles, but as a scholar, to be in places where also change was occurring. And at that point, I went to Guelph, and I was really excited at the 10 years that I spent there. And most recently, I spent 3 years at the University of Saskatchewan on a very large U15 school, and just watching programming innovation happening both from the academic and research side. And then about a year and a half ago, the opportunity to come to Laurier was there, certainly in the role that I have. But it also to be in a place where at this stage of my career, I wanted to be in a place that was very nimble, I felt, growing and really targeted for commitment to excellence in what we do in scholarship for our students and faculty. And that's kind of how I got here over the last, and been here for the last year plus. So it's been an interesting journey, both from balancing my scholarly activities and also the other pursuits that I've had in trying to make sure institutions have impact. So that's kind of how I've come here, both short term and then long term. I don't know if that answers it in that way, Jonathan.
Yep, that's great, Tony. Some might call it a circuitous route. Others might call it picking up lots of experience along the way.
Yeah, I think part of what I wanted to explain, and it was interesting. I saw in the audience, Kathy Cameron is here, and it was interesting when I began this route. And if I just share a story, we'll talk about it through the other questions that I'm sure are going to come up. I'm very much someone who believes in interdisciplinary research. And when I began my PhD studies, I had come from mathematics. I'm really a mathematician in engineering clothing, or an engineer in a mathematician's clothing. And at Waterloo at the time, I was working in electrical engineering, and I'm still working on the problems of circuit design. And the problem I was looking at was a combinatorics problem. And I had the good fortune at that time, because Waterloo has such a strong combinatorics and optimization department, which is part of the Faculty of Mathematics, that I was able to meet Jack Edmonds and actually Kathy Cameron. And we talked about partitioning, graph partitioning, which was really, how do you break up a circuit into its clustered components, which is now used in AI technologies in making decisions, which I didn't know at the time. And I had no idea about combinatorics in that area of mathematics, but it just excited me about what it could become. So that was and quite often when you're doing interdisciplinary work, you mentioned Circuitous, Jonathan, you feel like you're in a demilitarized zone where you're getting shot at from both sides. So I never felt completely accepted by the, at times, mathematics audiences I was trying to publish in, and certainly even the engineering audiences, until you showed them it could work. And so you always were taking this route, but you had to have a focus on where you were going. So, and that's sometimes the price of interdisciplinarity, which I understand very well when I see with my colleagues here at the university and other universities. So that's kind of how I got here. So I hope that that's putting some texture to this.
Yeah, no, it's great. So you mentioned, you mentioned your research interest in circuit design. How would you sort of describe the broad area of scholarship that you work in? Maybe what are some of the kind of research questions that you're interested in?
Thanks for that. It's interesting. I started in circuit design about almost 35 years ago. And fundamentally at the core, and I'll make it simple. If you take, all of us have laptops, all of us have computers, phones, cell phones. There's always a computer chip that drives that technology, which right now is a shortage because of the pandemic, but that's another story. But in that computer chip, if you think about it, what you're looking at is throwing up those transistors or up in the air, making them land on a two-dimensional board, or it could be very layered to be wired in a way that is as efficient as possible so you can deal with the speeds that we need for an application that you see in front of you that's very visual and requires a lot of bandwidth, etc. At the core of circuit design is making sure you make the transistors, you place them in the right place, the optimal location, wire them the same way so you don't have any hot spots. When a laptop's on your lap and it's very hot, likely the chip has not been wired right, and that's 90% of the chips or more. So what you want to do is design it efficiently so that it's the computer or the system you're trying to run, nuclear reactor, plane, whatever it is running with that chip that's reliable, safe, and efficient. And to do that, I was mentioning mathematics. It's really a combinatorial optimization problem. So when I started in the 80s, early 80s, the computer chips that Intel and the giants AMD were developing of the day, IBM, were maybe 100,000 to 1 million transistors. Now they're approaching trillions of transistors. So the magnitude of the problem has not only amplified in what you're trying to solve mathematically to get the optimal solution in where the transistors need to land, but how you wire them at the same time. And the other thing that's interesting now, speaking of interdisciplinarity, this is the science part, it really crosses over into physics in a major way. So what's happening with nanotechnology as these chips get smaller because of what we're trying to achieve is these, if you think about it, just a line, a wire, they get very close to each other, almost at the atomic level. Wow. And the concern from a physics perspective is that the electron can flip from one wire to another. And if, wow. If it's not designed right. So if you think about that, it has serious implications, because if that chip is actually going into a nuclear reactor and it should be off and it turns on at the wrong time because of a bad design, you can see what the implications are. So the challenges for computer designers, chip designers now has really amplified. And indeed, companies like Intel and other manufacturers in Asia primarily actually hire a lot of physicists to actually work with computer scientists, electrical engineers, and other even mechanical engineers now to actually solve these problems in a very holistic, together way. And the work that I'm still able to do, it's working with these very synergistic groups where I would solve the mathematical optimization problem, and the physicists and other scientists really work on the actual design so that that chip performs as intended, especially in very important applications that need security, reliability, whatever it is. So that's the challenge that's evolved in 40 years later, 35, 40 years later, that we're dealing with. So it's interesting. It's not just technology. It's how people and the science now have to work together to solve these problems, which is quite fascinating, I think. So.
In that interdisciplinary vein, I once heard somebody, not you, heard actually, I think it was some of your colleagues, describe one aspect of what they're trying to do in chip design as like you have a really good, mathematical optimization process. It does. It sorts lists or something, and one of the things that they were trying to do is to take that from software and design it into the hardware.
Mhm.
I guess that's because it makes it faster. Is that right? If it's wired in rather than
Yeah, I think, yeah, actually, Jonathan, that's an important point. The best systems, if you want to look at it, or outputs of systems, is the integration of the hardware and the software. A good example, nobody really states it this way, but everyone knows Stephen Jobs and Apple, and certainly the devices they produced. But if you look at an iPhone or an iPad, a Mac computer, Stephen Jobs and the teams of designers, engineers, and scientists that worked for Apple did that in a very unique and powerful way. Those teams really worked at integrating the hardware and the software algorithms that drove the applications. And Stephen Jobs is the leader. He got the engineering. He also knew the other part of how you sell it and have societal impact and cultural impact. It was that integration that really works the best. And I think more companies or successful applications, Jonathan, actually do that going forward. AI is the latest, where we look at artificial intelligence, and you look at the algorithms in artificial intelligence, which are indeed search or sorting algorithms at the core. The hardware they're mapped into and the specifics of that really allow that to do the magic in real time, where you want a decision to be made because of sensitivities. That's a good example that I can highlight where it goes.
There's another follow-up from your first answer was, you talked about making chips more efficient. I'm not even sure I'm using the word chips right here. Circuits more efficient. Is that also related to how fast the chip processes things, or is it more around energy use or something like that?
It's a combination. It can increase the speed. Chips, as depending on the technology you're using, are set up to a maximum speed that you can actually push the electrons through to trigger an action or that you want, or an outcome. How you design the circuitry or lay it out actually can slow that down to almost a quarter of that speed if you do it poorly. So it can have a huge impact just on what's called the routing, the placement, which is the transistors, and the routing, which are at the core. I mentioned earlier the partitioning, how you compartmentalize the chip and saying, okay, a quarter of the chip and the transistors are doing these activities. Why don't we put them together over here? And if there's a breakdown, it's isolated into a part of a chip, and you can do duplication in another part, because if there's a fault in the chip, especially in a key application of running an airplane or a nuclear reactor, a bridge mounting or whatever, you want to make sure that there's backup systems in that. So it's all this efficiencies that can be built into, and duplication that you want to put into it to make it work. But it does affect the speed. And right now, what's interesting for me in watching students, even at the undergraduate and graduate levels, that are coming out of not only technology program, the ones that integrate with the visual part, which are the artists and the creative elements that you see in many corporations, they really work in a very integrated way to solve these problems together. So even the ones who might have more of a arts or STEAM background really can appreciate what is happening on the engineering and computer science side. It's the true interdisciplinarity, and something as an educator that excites me, that I always want students not to get it after the fact, if we can do it as they're here, in universities and understand that a little bit, it can excite them and move them to really, where they need to be for the future, I think.
So Tony, what motivates or inspires your research?
What I like, and I hope I know there's a lot of researchers on this virtual call. What I like is going to the bleeding edge of a problem and really seeing how far I can push it to get to the next level. And what's important in that is that you're able to take risks. And I've always, through my career, always had enough where I knew, okay, I got to publish this to get tenure and all the things we have to do in the machinations. But I always left the real problems that I wanted to solve to get me to that bleeding edge. I've always took time to say, that's the problem I really want to look at, because everybody's seen this stuff, but they haven't really seen this, but they say that's where we need to go. And a term I've used, I stated before we got on this call, Jonathan, is you need to have a holy grail in mind. What's the really hard problem that will open up other areas of solution, not only in the discipline you're looking at, but could lead to applications that will have impact elsewhere. I'll give you an example, and that's what really drives me. The problems I solve, which are very combinatorial in nature, just a simple fact that if I have 1 trillion transistors and I have on the chip a spot where I can drop it in, it's a 2 to the trillion solution of who goes into all these holes as we lay it out. So you can't solve that optimally in real time. The question then, and this is the holy grail, is if you look at algorithms, optimization algorithms, and there's a class of algorithms now that are really used not for combinatorial optimization, but they're used for what is called continuous optimization. Not that something's 0, 1, but in the middle. There are a class of algorithms that were generated by a number of researchers, led by one in the early 80s, Narendra Karmarkar, that are called polynomial time algorithms that run in a fixed amount of time that you can solve problems like that optimally. The trick is, and this is the holy grail, is to get those solutions that are going to be between 0 and 1 to flip into a corner, to flip to a 0 or to a 1. So how can I design, and that's what I focus on, algorithms that move a lot of the solutions to look very combinatorial in nature, but are running in polynomial time. And that's the holy grail, right? And the fact is, there are algorithms where you try to get within 5% of the optimal solution of these combinatorial problems. Those problems are called NP hard. That means you'll never find even or guarantee that you're within 5% of optimality. The class of design problems I look at, many of them are in that category too. So they're just impossible to solve. So you have this problem. We are designing circuits with 1 trillion transistors on them. Is what you try to do is then use the mathematics, use the science and engineering and technology to start at a place, run a solution in polynomial time, and then look at what you might be able to achieve to gap it. In other words, to show, I think I can show that I'm within 10% of the answer, but I don't have to go all the way, because this answer I have from the engineering side will work extremely, extremely well. So that's when I was joking about the demilitarized zone, is where a pure mathematician would say, well, that's not an optimization problem. Technically, it's not. And the engineer is saying, now, what are you doing with the mathematics over here to get to that? So you have to convince the audience or the people you're trying to sell that design and application on the engineering side that this makes sense. And also on the pure side, we're very mathematical, the value of the type of work that you're doing and its impact. So that's where I like to be. And that's I'm trying to explain the outer limits or the bleeding edge I don't know if that's clear.
Yeah, I think that's great. So that's the sort of organizing big question that you're driving towards. You mentioned earlier that your work is very interdisciplinary or multidisciplinary, and not necessarily, but often along the lines of interdisciplinary comes collaborations. I assume your work is collaborative. Maybe I'm wrong in that, but I sort of assume it is. And if it is, do you tend to collaborate with, lots of people on one-off projects, or do you have some collaborators that you work with or you have worked with for long periods of time?
There's a number of collaborators I've worked on, certainly a long period of time, but I've also worked very strongly in these groups that I've mentioned in a very synergistic way. I was fortunate when I was doing my postdoc, when dinosaurs roamed the earth, way back when. I won't completely date myself, but the Montreal Canadiens stopped winning Stanley Cups. Anyway, that was, maybe I'll date myself that way in the 80s. But I had the good fortune to work with a group at IBM. I had a postdoctoral fellowship, an IBM postdoctoral fellowship, and I was able to take it up at IBM in a mathematical sciences division. But it was 50% engineers and computer scientists, and then optimization people were the other half. And it was a fantastic group that I was in. As the postdoctoral host, his name was Bob Brayton, and Earl Barnes, who was part of the group, was the optimization guru, and Bob Brayton was the engineer. And he had a wonderful past from Berkeley, where he was a faculty member, and then went to work with IBM on circuit design problems and optimization problems going forward. It was interesting to show how that group worked, and then I'll give some other names. Ralph Gomery, who was the director of the Thomas J. Watson Research Labs, which was the main research labs for IBM, came into our group when they called us into a meeting. And this is Bob Brayton's group. And we're circuit designers, optimizers, all there. And he brought us in and said, all right, Exxon has threatened to pull their mainframe computer contract with us unless we solve their budgeting problem for next year. And it was like 100,000 decision variables, yes or no, do they do this or do they do that, and about 1 million constraints because of what the organization, it's a big organization. And they said, we need to solve this in 1 week, or we lose a multi-million-dollar, $100 million contract. And of course, you guys are going to do this in 1 week. So what was interesting, but after the panic set in, we stopped drinking. Which is true. We worked all-nighters for the week, but we actually had in Bob Brayton's group, we had the engineers and the mathematicians that had been working together on a different problem. But it turned out the problem they were mapping into, and that's what our director, Ralph Gomery, had sold them on. He says, I think it's very related. He knew the mathematics of the optimization problem. It was very close to the circuit design problem. So he guessed we had a shot at this and was willing to risk other things. He was right. So within about 2 days, the optimization group, which I was part of, worked out a modified algorithm to solve this size of problem, because it was way beyond, we didn't have a Big Blue or that supercomputer IBM had at the time, but we had an ability then to solve that and find a solution. And then with the engineering application side, we were able to do the mapping into the Boolean solution that we needed going forward. And actually within 3 days, we had a very good answer to what they needed. We refined it. We then brought it upstairs, discussed it with the director and everyone. And it set the tone, because that group then won an IBM award for what they did. Because they performed, we got extra budget to hire people. That was cool. and because of what they performed. So it's all great stuff, and it really framed what I did. I've always done with my graduate students, postdocs. I would take mathematicians, engineers, my colleagues. In particular, I can mention Miguel Anjos, who's at École Polytechnique right now, is in the engineering school. Miguel is a wonderful mathematician engineer and really deals with semi-definite programming, which is an extension of continuous optimization into different types of problems, including combinatorial problems. I work with him regularly, not as much as I would like in the last few years. And Tomas Terlaki, who was working at Lehigh University in the States, in Pennsylvania. I worked with him quite extensively in his group. And of my colleagues, I'm mentioning these two, there are others. We always work in this way. Their students, my students, postdocs, we would share postdocs. We worked in this very synergistic, integrated way, and it's led to some fantastic publications where we when you put multi-authors on a paper, it's really legitimately equally shared, in terms of what we do. So that's reflective of the problems we solve and the relationships, professional relationships that are needed to make it work, I think, that I've maintained.
Tony, what would you say have been like one or your proudest moment, or one of your proudest moments as a scholar?
Yeah, sure. It was very little. Actually, it was interesting. It was just a conference presentation that I did. I had been working on one of these problems. It was a routing problem, a wiring problem. And Jonathan, to that algorithm I told you about, continuous algorithm to solve this problem in polynomial time, which was a combinatorial. I had come up with a very optimal solution and a way to do it very efficiently. And I got it published in a journal paper a year later, but I was test driving it at a Canadian conference, engineering conference, the Canadian Conference on Electrical Engineering, CCEE. And I think it was 84 or 85. So I was the last presenter in the last session. And I presented the paper, and unbeknownst to me, I didn't know this, there was an award that they would give for the best paper at the conference. And I wasn't paying attention to any of it. But I noticed my session, as I started speaking, it got bigger. Normally they fade out, they hear your present, I don't want to hear this, they leave, But it started getting bigger, and I didn't know what was going on. But what was happening is the adjudicators got wind that this presentation was taking part and it should have a look at it. And I wasn't paying attention, but my audience doubled in size pretty easily. And then at the end of it, we went to the dinner, and there was an awards part. And I wasn't aware of it, and I got the best paper, and it was just like not trying. I was just trying to get my work out, and it just surprised me. So, and it was in Canada. It was a sort of a national conference, but it was nice to see that with my colleagues. My students were there, and it was a solo authored paper. And then I did subsequent work with my students on it. So it was just surprising the way it worked. But the most important part was doing the work, and then getting some small recognition. I think was nice. So.
Well, that's a lovely story, Tony. Thanks for sharing that. Unfortunately, we've come to the end of our time. I feel like we could keep going for hours here. There's lots to be said, but I really appreciate you taking the time to share your scholarly passions with us today. I'm sure the audience joins me in thanking you.